All right, so reading through the Nelder and Wedderburn 1972 paper on generalized linear models, I'm going to start here at the random component and work through this first equation here. And what I want to do is I want to show that this is true. Okay, so let's start with reading what's going on here. So suppose our observations z come from a distribution with this density function. Okay. And this is an exponential family distribution that you're seeing here. And that's a fun exercise to kind of work through yourself, and I highly recommend it, where you can basically rewrite the normal distribution, the gamma distribution, other exponential family type distributions, and you can identify what the functions beta, h, g, and alpha are, and basically you can show that those are exponential family distributions because they can be written in this format. So that's just a fun side thing that you can do, or I could make additional videos showing later. Okay, so basically this is just a definition here. That's all we're seeing. Okay, so they work out that they're going to need that the first and second derivatives of the log likelihoods they're going to need these first two equations, okay, which are these results are found in a 1967 paper, which you can look up, or actually we're just going to start here and show this relationship is true. Okay, so what I've done here is I basically have written a lot of that introduction out, summarized it a little, and this is where I want to start. I want to show this relationship. Okay, I want to understand why this is true before I move on. So let's start with what is this L? This capital L in statistics. This is the log likelihood function. Okay. You will see statisticians write that capital L and assume that you always know that that's what it means. Okay, and as a side note, when we say log in statistics, it's very annoying, I know. We mean natural log. Okay, and that's just through history. I don't really know exactly how it came about. In math, they always write ln. In statistics, we just write log. Maybe we used to write log base e, but then we got lazy and dropped the e. I'm not sure exactly what happened there, but I do know that in statistics, we always mean natural log when we write log. Okay, so what is the log likelihood function? It's basically the log of our density function. Okay, so when, let's see what I'm trying to find here. I want to find the expected value of the derivative of the log of this density function. Z theta phi. Okay, d theta. Okay, so I'm taking the derivative with regards to theta, and I want to show that this is equal to 0. So let's figure out how. Well, what is it? Okay. So this first step, let's go ahead and find the derivative of this log. Now, another side point. Suppose I wanted to know the derivative with regards to theta of just ln of theta. Okay, so a much simpler derivative. So instead of it being a function, suppose it wasn't a function, it was just theta there. Well, from calculus, we know that this is equal to 1 over theta. Okay, so then if it's a function, then I need to first do this and then use chain rule and then find the derivative of that function, right? So that's the rule that we're going to use first. So this is going to be 1 over our function. Okay, and then the derivative of that function. So that's chain rule. Okay. Okay, so all I've done thus far is I've taken that first derivative with regards to theta. So now I need to know this expected value. Okay, so let's do another little side note. Let's remember what is expected value. Okay, so suppose I want to know what is the expected value of z. I would say, oh, okay, just take the integral of z and then multiply that by whatever the density function is for z, and then dz. Okay? Right? By definition, that's what expected value is. So instead of having just z now, right, instead of having just z, I have like all this jazz here. Okay? But I would still multiply it by the density function of z, which is that pi jazz. Okay? So let me change back to yellow. So this equals the integral, okay, of all this jazz, pi theta phi times the derivative with regards to theta pi of z theta phi, okay, and then multiply that by the distribution of z, which in this case is just pi z theta phi. All right, and I'm taking the derivative with regards to z. Okay, so this is the expected value with regards to my random variable, which is z. Okay. So I do see a nice cancellation right off the bat. Okay. We see that we have our density function in both the denominator and numerator, so they cancel each other. So I end up with the integral of a derivative. Okay. All right, so now what do I do? Well, from here, what I want to do is I want to reverse these integrals and derivatives, because I know the integral of a density function has to be equal 1. So this is what I want to do. Okay, I want to reverse the integral. I want to do the integral first and the derivative second, as opposed to the derivative first and the integral second. Well, can I do that? Okay, turns out I can, using Leibniz integral rule. Okay. In order to use this, I need to assume that the bounds of z do not depend on theta. Okay, this is a very, very important assumption, and it's something that needs to be remembered as you continue to work through the GLM, right? It's the reason why we can't use, for example, the uniform distribution, because the bounds of the uniform distribution would depend would depend on your random variable, right? So you can't. So you need the bounds of your random variable to not depend on your parameter theta. Okay, and then you can reverse your integration and your derivative. Okay, so then once you're here, the integral of a PDF or a density function is equal to 1 by definition of what a density function is. Okay, and then a derivative of a constant is 0. All right, so there you have it. We have shown that the expected value of the likelihood with regards to theta equals 1, right? That's what we wanted to show. Or sorry, not equals 1, equals 0. And of course I just moved my window. Okay. Right, which is what equation 1 is.